Hello, everybody. Welcome back to the Columbia Financial, whatever, and Risk Management course. This is the second lecture, so let's talk about Bayes' theorem. Let A and B be two events which B of B is non-zero, then the probability that A given B is equal to the probability that A intersect B over P of B. So I will note one thing that was not mentioned and that I was always sort of confused about. This is the definition of this weird symbol. And it kind of makes sense what it is, but anyway. So then it continues with a sort of derivation. So the thing is, how do you get from this to this? It's very straightforward. So P of A intersect B is P of B intersect A, and then we apply the exact same definition to get P of B given A times P of A. Hopefully that makes sense. And then finally he goes into this, which is just the bottom. He's replacing it with partition of AJ, so he's going over all the possible AJ and then doing this. So let's go over an example, and I'm going to go over what each of these three represent. So here's his example. So we're rolling two fair six-sided dice, and then x is the sum of the two die. So each of these squares, you can see the value of x, and then y1 is here, and then y2 is on this side. So let x equals y1 plus y2. Question: what is the probability that y1 is greater than or equal to 4, given that x is greater than or equal to 8? So by definition, this is equal to the probability that both of these are true. Y1 is greater than or equal to 4, and x is greater than or equal to 8, divided by the probability that x is greater than or equal to 8, right? The bottom one. So the probability that x is greater than or equal to 8, so the sum is like he illustrated, it's this. And then the probability that y1 is greater than or equal to 4 is this. All the numbers starting here like this rectangle. The probability that both of these are true are, you just count all the squares here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 over, and there's 36 squares total. And then on the bottom, the probability that x is greater than or equal to 8. There are, how many squares here? 1, 2, 3, 4, 5, 9, 12, 14, 15, I think. Hopefully I got that right. So 12 over 15, that doesn't sound right. Probability that y1 yeah, I think that's correct. Let me check. Let me go back to here. Is that the number he got? Sorry, I'm going to check. Let's see. Yeah, that's correct. Okay, perfect. So then this is not something he went over, but let's go back to this definition here. So what is probability of A? That's the probability that y1 is greater than or equal to 4. So another way we could write this top expression is, let's find the probability that y equals to 4, so all of these. And then what percentage of, and then yeah, so the probability of y, this is 1/2. Just going off by this definition here. And then what is, well, yeah, probability of B given A. I guess I know like conceptually what that means. So probability of B given A is just, so we know this is true, so then probability of B is this, that the x is greater than or equal to 8, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's again 12 over 1, 2, 3, 4, 5, 6. 12 over 20. Is that right? This cancels out. That can't be right. 6 over, yeah, somewhere. Did I calculate that right? 18? 18. But even that's not correct. Is that correct? Oh, this is 1/3. But then, did I already multiply it by? So on top I should get 12 over 36, right? 12 over... Yeah, that's what I get, right? 12 over 36. So 6 over 18, yeah, that's 1/3. Yeah, 12 over 36, that's correct. Okay. So let's go down to here. Continuous random variable definition. A continuous random variable x has probability density function PDF f if f of x is greater than or equal to 0, and for all events a, probability x is in a. So this obviously assumes a lot about f of x. We're definitely assuming that f of x is continuous, and that a is a subset that it's integrable over. Like it can't just be like any subset of the real numbers. So yeah, the CDF and PDF are related by f of x is, let's see, am I still recording? Yes, I'm fine. Are related by this. So he went over the definition. So the f of x, what is the definition of f of x? It's the probability that x is less than or equal to, sorry, the random variable x is less than or equal to x. And then this is equal to the probability that x is greater than negative infinity and less than or equal to x. And then by definition, this set is a. So then we do, should be an integral from negative infinity to x f of y dy. So then this thing, it is often convenient to observe that. So the thing is, it's a continuous random variable. So it's the probability density function. It's a continuous function now. So you can't just like, I mean, f of y is an actual function that you can get the point of, but the probability density function, let's just say it's like the normal there. If you what am I trying to say here? Yeah, if you take this integral and you make it like really small here, then you're going to get like approximately 0, right? If you make this a very small, you can't just like isolate a point. What you want instead to say is what is the value of the function, and the value of the function is, you're going to try to isolate the point, but you got to make sure that if you pick out a very small slice, you got to multiply by the epsilon, the size of the slice. So that's what this is saying here. So the way I'm going to approximate this point here, given that I have this, so I'm not sure what f of y is, but given that I have this, the way I'm going to approximate f of y is by picking a very small slice with radius epsilon, and then I'm going to I'm going to integrate this, and the average integral of this slice is going to be around this, for obvious reasons, because it's continuous, and continuous functions are whatever, they approximate the point when integrated. Okay, the normal distribution. We say x has a normal distribution, or x, if this is true, the mean and variance of the normal distribution satisfy this. So I wanted to prove this fact, so let's go with it. He didn't define yet how to do this, but I know the definition. So this should be x times this f of x, so whatever, this whole thing, sigma squared exponent of x minus mu squared over 2 sigma squared. Okay, so how we're going to do this, we're going to integrate by parts. So let u is equal to x minus mu. So then this x gets replaced by a u plus mu up here. And then we're going to take this out of here. And then we're going to keep this. So then here's that constant. I don't want to write it out. And then e to the x minus mu. Actually, sorry, replace this with u squared over 2 sigma squared. Okay, so now we're going to integrate by, is it integrate by part? We're just going to, the integral of two functions is equal to the integral of one function plus the other function, right? Assuming whatever assumptions we have about functions being integrable. So yeah, the point that I'm trying to make here is that this this u, when you integrate this function, so when you integrate the first function, so u times e to the, honestly, it's like minus u squared divided by 2 sigma squared. When you integrate this function, you end up with integral, not integral, you get e to the minus u squared over 2 sigma squared. Then there's like a constant here that I don't care about. And then it's from positive infinity to negative infinity. But if you put in positive infinity here, you get 0, because this is u squared is infinite, and e to the minus of a very big number is 0. And the same thing goes for minus infinity because it's squared. Therefore, the integral for both is like the integral, when you calculate it, is 0 minus 0. So basically this integral, this whole thing is 0. And then you do the second part by parts. And this mu, basically I'm just going to unsubstitute it, if that makes sense. I'm just going to like not substitute the second part. So then we have negative infinity, infinity, and I'm going to bring the constant back in. So I just basically don't want to calculate this integral at all. I just want to get exactly the same integral here from up here. And I know that the integral of this is equal to 1. This integral from negative infinity to infinity is equal to 1. So this, whatever, e to the minus, I'm going to undo it. Obviously I forgot there's like the whole d mu when I do a substitution by parts, then I have to say if u equals x minus mu, then du is dx, and then the mu goes away, but whatever. Dx, so this is equal to 1, so we just end up with mu. Hopefully that makes sense. Finally, we're going to talk about the log normal distribution. We say x is a log normal distribution if log of x is, so we take the log of this distribution and it's approximately normal. So I've never seen this distribution before, so I wanted to see what it looks like. So as we know, the log of, I would say the ln of a negative number is undefined. Negative is undefined. And then the ln of 1 is equal to 0. And then the ln of any number greater than 1 is greater than 0, and the ln for x between 0 and 1 is negative. So basically what this distribution looks like here, we have this, and then we have this 1 here, and then I would imagine it looks something like this, and then I don't know what this constant is, some constant here. But then this is the upper point because it's a normal distribution. As soon as hit this, it just kind of goes like that until negative infinity. And hopefully the area under this curve is sums up to 1 because that's the definition of a distribution. So hopefully that makes sense. When you take the ln of this, there's very few numbers that are negative infinity according to the normal distribution. So a number here is going to correspond to negative infinity in this direction. And then we assume that we take the log of the distribution, we get the normal, right? So a number that's very close to 0 is going to be very, very negative, so there's going to be very few of them. And as we get closer to 1, That's where we're going to hit the 0 because we take the ln of 1 and we get 0. So that's the hump. And then there's lots of numbers here. And then there's fewer, but I think the drop off is slower because it should be slower. I can try to look that up later. Okay, that's it. Thank you very much. See you next time.